Hello friends, so today we are going to solve the question from modern physics, and these questions are from the year 2008. Total 3 questions. 2009 also 3 questions, and from 2010 2 questions. So in totality we are going to solve 8 questions. So the first question, it was asked in the year 2008, and it states that in a mixture of H and H positive gas, He positive gas, He positive slightly ionized He atom, and H atoms and He atoms are excited to their respective first excited states. Subsequently, H atoms transfer their total excitation energy to He positive ions by collision. Assume that Bohr model atom is exactly valid. So based on this, we are having these 3 questions. In the first question, it states that the quantum number n of state finally populated in He positive ions. In part B, the wavelength of the light emitted in the visible region by He positive ions after collision with H atoms is. And part C, the ratio of kinetic energy of n is equal to 2 electrons for H atom to that of He positive ion is. So here H is of hydrogen and He positive is slightly ionized He atom. So in this case, we are given that whenever there is a collision between H atoms and we have He positive ions, the total energy is being transferred. Okay, so this is, you can say, main consideration here. So we can write that on collision, the energy, let us suppose that is our delta E associated with our hydrogen, will be transferred to our delta E to that of our helium. Okay, so let us find out the respective energies, and first of all we are going to find out the energy released by H atom, and which we are going to call it delta He, and energy released by H atom, which is our delta EH. This will be equal to our 3 by 4 multiplied by 13.6 electron volt. And whenever the helium gains this energy during collision, let us suppose that it goes to the nth state. So you can say that let He positive go to nth state, therefore energy required, and that energy required we just called as delta He, energy required we can see our delta EH will be equal to 13.6, and we have Z square, that is multiplied by 2, and we have here lower state is our 2, and this comes as nth state is a square, and this is our in terms of our electron volt. So we have both our delta EH as well as delta HE, and we equate them. So we can say our 3 by 4 times 13.6 is equal to, it has to be 13.6, not 13.4. 13.6, and this will be 4, and we are left with 1 by 4 minus 1 by n square, and here this 13 by 4 cancels out, and this gives us 3 by 16 is equal to 1 by 4 minus 1 upon n square. So we get this as 1 upon n square is equal to 1 by 4 minus 3 by 16. 16 will be LCM, so this comes as 4 minus 3, giving us 1 upon 16, or from here we can say value of n square will be equal to 16, thus giving us that the value of n is equal to 4. So option C is correct, and this is part A. Option C is correct. Next, in part B, the light emitted in the visible range. So part B, and so we can easily find out the difference in energy. Okay. So we can say that our energy difference, let us suppose our that is our delta E, will be equal to energy of the fourth minus energy of the second. So we substitute the value, delta E will be equal to minus 3.4 minus of minus 13.6, and this gives us 10.2 electron volt. And from here we can just quite easily find out our wavelength. So we can say the wavelength lambda will equal to hc upon delta E. hc we can write in the format of our electron volt, that is our 1242, and here we have 10.2 electron volt, and this wavelength will be coming close to 122 nanometer, but this is not in visible range, not in visible range. Okay. And for this calculation we assumed that initial value of n was over 4 and final value of n was over 2. Okay. So for this range the wavelength is not in visible. Now we say that our value of n is, initial value of n is our 3, and it transition to the final value of n is equal to 2. Therefore, once again we find out our delta E, which gives us our E of 3 minus E of 2, giving us minus 6.04 minus of minus 13.6, which will be equal to 7.56. Once again, we are going to find out the wavelength. That's our lambda will be equal to hc upon delta E. hc is 1242 and this is 7.56, and this gives us approximately 164 nanometer, but this still is not in visible range. Not in visible range. Okay. And so we are going to try for our, now n is equal to 5 to n is equal to 2, and from here we can write our delta E will be equal to E of 5 minus E of 2. E of 5 is our minus 2.176 minus of minus 13.6, and this gives us that our delta of E will be coming as 3.864 electron volt. And once again the wavelength lambda will be equal to 1242, and this is about 3.864, which is approximately equal to 321 nanometer, and this is a representation of our ultraviolet, but we are required to for the visible. So therefore we write for n equal to 4 to n is equal to 3, and once again our delta E is equal to E of 4 minus E of 3, which gives us 6.04 minus 3.4, giving us 2.64 electron volt, and the wavelength lambda will be equal to 12.42, this is about 2.64, which gives us approximately equal to 470 nanometer, and this is our visible range. Therefore, we can say that the wavelength will be approximately equal to option C, that is about 4.8 10 to the power minus 7. Option C is correct. Next question, part C. It states that ratio of the kinetic energy of n is equal to 2 electron for the H atom to that of He positive ion. So part C, we have to find out the ratio of their kinetic energy, and directly we can use the Bohr model formula. So we can say for Bohr's model, kinetic energy is equal to 13.6 Z square upon 2n square. And we can write this for hydrogen as well as helium and separately, same formula. So we can say for hydrogen, whose value of Z is equal to 1 and value of N is equal to 2. So we get kinetic energy of hydrogen will be equal to, we have this as 13.6 multiplied by 1 square and divided by 2 multiplied by 2 square, that is 4. So from here we get kinetic energy for the hydrogen will be equal to 1.7 electron volt. Similarly, we write for our helium ion. For He positive, value of Z is equal to 2 and value of N is also equal to 2. So kinetic energy for helium ion will be equal to 13.6 multiplied by 2 square, that is 4, 2 multiplied by 4, and this comes as our 6.8 electron volt. Now simply we can just find out their ratio. So kinetic energy hydrogen, kinetic energy helium positive will be equal to 1.7 divided by 6.8, which comes as 1.1 by 4. And that was our requirement to find out their kinetic energy. That option A is correct. A is correct. Next question. It was asked in the year 2008 and it states that a radioactive sample S1 having an activity of 5 microcurie has twice the number of nuclei as another sample S2 which has an activity of 10 microcurie. The half-lives of S1 and S2 can be. So here we have two samples S1 and S2 and their activity is given to us as 5 and 10 respectively. So we can say that for sample S1, let us suppose we call this activity is A1, which will be of 5 microcurie, and we have for sample S2, let us call that activity as A2 and that is given as 10 microcurie. And it said that radioactive sample is twice, and for sample S1 let us call this N1 and for S2 let us call this as N2, number of nuclei. So we can say that number of nuclei will be giving us a relationship that our N1 is equal to twice of N2. Now we can just use our radioactive formula and solve it. So we have radioactivity formula which tells us that our A will be equal to lambda times N, and lambda is our natural log of 2 divided by its half-life multiplied by N. So we have two samples and the activity are A1 and A2. So we can write our A1 will be equal to natural log of 2, half-life of first, let us call this as T1, and this have N1. Second we can write A2 will be equal to natural log of 2, half-life is T2 multiplied by N2. we take their ratio. We can write our A1 upon A2 will be equal to, and this we get as natural log of 2 multiplied by N1 divided by T1 multiplied by natural log of 2 N2, and this is our T2. Here this natural log of 2 cancels out, and this gives us N1 upon N2 multiplied by T2 upon T1, and N1 is equal to twice of N2. Therefore we can write that our A1 upon A2 will be equal to twice of N2 divided by N2 multiplied by T1 upon T2. And we already know A1 and A2. A1 is our 5, A2 is our 10, and here N2 and N2 cancels out, so this comes as 2 into T1 upon T2, and we can just sort it out. So we get this as T1 upon T2, or we can just also cancel at this 10 goes by 2. So we get T2 is equal to 4 times T1. Once again, sorry, this is T2 by T1. So we get that our T1 is equal to 4 times T2. So one by one we can check the options and try to justify this relationship that our T1 should be equal to 4 times T2. Okay, so this is, from here we can say this option A is directly able to satisfy this particular relationship. So option A is correct. A is correct. Next question. It was also asked in the 2008, and it states that in a radioactive decay chain, thorium nucleus decay to lead nucleus, let n alpha, n beta are the number of alpha beta particles respectively emitted in this decay process. Which of the following statements is or are correct? So here we are given that our thorium, that is our 232 and 90, it decays into our lead, which is our 212 and 82. And this decay is in terms of alpha as well as in beta particles. Okay. So it means two type of decay are going on. One is alpha decay, another one is a beta decay, respectively for the alpha particle as well as for beta particle. So we can say that alpha decay and in this case of our alpha decay, helium, we have this is 4 as well as 2. So basically means that the mass number will be reduced by 4 and atomic number is reduced by 2. So we can say mass number decreases by 4 and atomic number decreases by 2. And we have our beta decay. And this beta decay, the atomic number increases by 8 and one second. So from here we can say that the change in mass number is our 20. We have this as 232 minus 212, so this change in mass number is 20, and we know that the mass number decreases by 4. Therefore we can write that number of alpha particle will be equal to 20 divided by 4, giving us 5. And because of the same number of, you can say, alpha particle, the charge is Z will change by 10 units. 1 second. Yes. So we can say that therefore due to 5 alpha particles, Z will change by 10 units. But the given change is our of 8 units, that is our 90 minus 82. So we can write that the given change is 90 minus 82, that is our 8. Therefore the number of beta particles is 2. Number of beta particles is 2. So this is our number of alpha particles, and this is our number of beta particles. Alpha particles is 5 and beta particles is 2. So option A and C are correct. A and C are correct. Next question. It was asked in the year 2009, and it states that the photoelectric experiment photoelectric effect experiments are performed using 3 different metal plates P, Q and R have a work function as phi of P 2, phi of Q as 2.5 and phi of R 3 electron volt respectively. A light beam containing wavelengths 550 nanometer, 450 nanometer and 350 nanometer with equal intensity illuminates each of the plate. The correct IV graph for the experiment is. So here we are having three different work functions, or three plates are there and they are having three different work functions. So we are given a work function of plate P is our 2 electron volt. Work function for plate Q is given as 2.5, and work function for R is given as 3 electron volt, and their respective lengths are also given. Respective wavelengths, let us suppose they are lambda 1, lambda 2 and lambda 3. So we can say for P, let us suppose that lambda 1 is 550, for Q, that is lambda 2, is our 450, and for lambda 3 it is 350 nanometer. And it is also given the intensities for all the wavelengths are equal, and from there we are supposed to find out the graph. Okay, and the graph is plotted between I and V. So first of all, we are going to find out the energy of each photon. So we can say our E1 will be equal to, we have this as product of HC is 1240, so we can write this as 1240 upon 550, and this comes as approximately as 2.25 electron volt. Similarly, we can write our E2 will be equal to our 1240 divided by 450, and this gives us approximately as 2.76 electron volt. And we have our E3, which is our 1240, and this is our 350, approximately coming as 3.54 electron volt. Now this is the energy associated with each photon. And so if you make a comparison between the energy E1, E2, and we have E3, that is our 3.54 electron volt, and the respective work function, so we can say that, let me write it here, comparing respective photon energy with the work function. So our E1 is our 2.25, and work function for the plate is our 2 electron volt. And from here we can say that our E1, E2 as well as E3 are greater than our work function for the plate P. So we can say our E1, E2 as well as E3, all these are greater than the work function for plate P. Therefore, we can say that the wavelength lambda 1, lambda 2 as well as lambda 3 cause emission. and for our phi q is our 2.5, and for this case we can say that our E2 and E3 are only greater than our phi of q, because our E1 is 2.5, our E1 is less than phi of q. Therefore, lambda 2 and lambda 3, these cause emission. And finally, we are having 3 electron volt, which states that our E3 is greater than our phi of r, and both E2 as well as E1 are less than phi of r. Therefore, only lambda 3 results in emission. And we also know that if you compare their saturation currents, so the saturation current is proportional to the number of emitted electrons. So we can say comparing saturation currents, and we know that saturation current is proportional to number of emitted electrons. And we just concluded that plate P emits electron for all the 3 wavelengths. Plate 2, that is our Q, emits only for 2 wavelengths, and plate R emits only for 1 wavelength. So we can say that our plate P emits electron from 3 wavelengths, and plate Q emits electron from 2 wavelengths, and finally we have plate R emits electron from 1 wavelength. So quite obvious, if the saturation current for P plate is our IP, for our Q plate is our IQ, and for R plate is our IR, therefore we can write that our IP will be greater than our IQ, will be greater than our IR. Now we can also compare their stopping voltages. Stopping voltages, and stopping voltages can be determined by the maximum kinetic energy of the emitted electrons. Maximum kinetic energy of emitted electrons. Therefore, plate P, we have key max for P plate will be equal to, and this is our energy max for pre-plate minus work function for p-plate. This gives us 3.54 minus 2, so we get our K maximum for p-plate will be equal to 1.54 electron volt. Similarly, we can write for plate Q, which is our kinetic energy maximum for plate Q will be equal to maximum energy for plate Q, that is our .54 and work function 2.5. This gives us 1.04 electron volt. And finally we have our plate R, that is our K max for plate R will be equal to 3.54 minus 3, giving us 0.54 electron volt. Therefore we can say that stopping potential for P is greater than stopping potential for Q is greater than stopping potential for R. Therefore, and saturation we just found out is also our IP is greater than IQ upon. So it means it will be graphically, we can say our P will be greater than Q will be greater than R. And this is true for both our stopping potential as well as our saturation current. So our option A will be correct. Option A is correct. Next question. It was asked in the year 2009 and it is basically a passage type question, and it states that scientists are working hard to develop nuclear fusion reactor. Nuclei of heavy hydrogen, that is 1s2, known as deuterium and denoted as by D, can be thought of as a candidate of fusion reactor. The D to D reaction is 1s2 plus 1s2, giving us 2h3 helium plus a neutron and plus energy. In the core of fusion reactor, a gas of heavy hydrogen is fully ionized into deuteron, nuclei and electrons. This collection of 1h2 nuclei and electrons is known as plasma. The nuclei move randomly in the reactor core and occasionally come close enough for nuclear fusion to take place. Usually, the temperature in the reactor core are too high and no material wall can be used to confine the plasma. Special techniques are used which confine the plasma for a time t0 before the particles fly away from the core. If n is the density, that is number divided by volume of deuterons, the product n t0 is called as Lawson number. In one of the criteria, a reactor is termed successful if Lawson number is greater than 5 into 10 to the power 14 second per centimeter cube. So based on this, we are having 3 questions. In part A, the core of nuclear fusion reactor, the gas becomes plasma because of. Part B, assume 2 deuteron nuclei in the core of fusion reactor at temperature T are moving towards each other, each with kinetic energy of 1.5 kT, where the separation between them is large enough to neglect Coulomb potential energy. Also neglect any interaction from other particles in the core. The minimum temperature T required for them to reach a separation of 4 into 10 to the minus 15 meter is in the range of. And for part C, the results of calculation of the 4 different designs of fusion reactions using D to D reactions are given below. Which of the following is most promising based on Lawson criteria? So first one is quite straightforward, and it says that the core of nuclear fusion reactor, the gas becomes plasma because of the high temperature inside the reactor. So this is quite straightforward, because at very high temperature the thermal energy is large enough to overcome the electrostatic force of attraction between the electrons and nuclei, and that result in the ionization. So we start with part B. And part B, we are going to use our conservation of energy, which basically means that the loss of kinetic energy will be equal to the gain in their potential energy. So you can say conservation of energy we have loss of kinetic energy of two D nuclei will be equal to gain in their potential energy. Gain in their potential energy. So their loss will be equal to 2 into 1.5 times kT will be equal to, and the gain will be equal to over 1 upon 4 pi epsilon naught multiplied by Q1, Q2 and divided by distance between the two, that is our 4 into 10 to the power 15 minus 15. And we substitute all the values, we get this as 2 into 1.5, K is our, we require this as, one second, we need to find out temperature, okay. So we can write this as 8.6 into 10 to the power minus 5 multiplied by T will be equal to, we have this as 1.44 into 10 to the power minus 9 divided by 4 into 10 to the power minus 15. We can just straightforward solve it because we know each and every value, and this gives us that the value of T will be equal to 1.4 into 10 to the power 9 times K. So therefore the option A is correct. A is correct. And part C, we have to find out 4 different designs, and we are going to compare it with the Lawson criteria based on these 4 options. And for the option A, value of n is given as 2 and the confinement time is given as 5. So we can easily find out the Lawson number, which is n times T naught. So we have option A. Option A gives us that value of n is our 2 into 10 to the power 12, and we have our T naught is our 5 into 10 to the power minus 3. So from here we can find out our Lawson number, which is our n times T naught. This will be giving us 5 to the 10, so this comes as 1 into 10 to the power 10. Option B, we have our value of n is our 8 into 10 to the power 14, and our T naught is our 9 into 10 to the power minus 1. So once again we can say our Lawson number will be equal to n times T naught, giving us 8, and it will be becoming as 72, that is 7.2 into 10 to the power 14. Similarly, we have option C, value of n is 4 10 to the power 23, T naught is our 1 into 10 to the power minus 11, and from here we get Lawson number n times T naught, giving us 4 into 10 to the power 12. And finally we have our option D, value of n is our 1 into 10 to the power 24, and value of T naught is our 4 into 10 to the power minus 12. So we get our Lawson number will be equal to n times T naught, and this is our 4 into 10 to the power, this will be coming as 24, and 12, so this will be coming as 12. And we are given that the most promising Lawson number is given to us as 5 into 10 to the power 14 second per centimeter cube. So if you make a comparison between all these options, you can see this option number B is greater than our 5 into 10 to the power 14. So option B is correct. Because this given Lawson number is acting a kind of a threshold. So anything that will be greater than the threshold will be the correct option in this. That was option number B. Next question. It was also a passage type asked in the year 2009, and it states that when a particle is restricted to move along x-axis between x is equal to 0 and x equal to a, where A is a nanometer dimension, its energy can only take certain specific values. The allowed energies of the particle moving in such restricted region corresponds to the formation of a standing wave with nodes at the end x equal to 0 and x equal to a. The wavelength of the standing wave is related to linear momentum p of the particle according to de-Broglie relationship. The energy of the particle of mass m is related to its linear momentum as E is equal to p square upon 2m. Thus, the energy of the particle can be denoted as a quantum number n taking values 1, 2, 3, where n is equal to 1 is called ground state, corresponding to the number of loops in the standing wave. Use the model described above to answer the following 3 questions for the particle moving in a line x equal to 0 to x equal to a. So here we have 3 questions. In question number A, it states that the allowed energy for the particle for a particular value of n is proportional to. For B, if the mass of the particle m is 1 into 10 to the power minus 30 kg and A is 6.6 nanometer, the energy of the particle in its ground state is closest to. And in question C, the speed of the particle can take a discrete value proportional to. So here it is a combination of basically, you can say that the movement of the particle along with our standing wave formation. And it states that at x equal to 0 and x is equal to a, there are nodes. So obviously rest will be alternating between node as well as antinode. So we can just draw an approximate figure. So suppose this is our x equal to 0 and this is our position x is equal to a, and here we are given that these are nodes and the distance between them, between this entire, or we can say length of the string ideally, is nothing but our a. So this distance is our a, and there will be alternation of node as well as antinode. So first is node, so second will be antinode, similarly node, and here also we are going to have our antinode as well as node, and this process is going to continue. So we can say that alternate nodes and antinodes exist in the region x equal to 0 and x is equal to a. And we can say that for our nth mode there will be n nodal points. So you can say in nth mode we are going to get n nodal points, and therefore the wavelength of the stationary wave suppose that is given as lambda of n, then we can write that n times lambda of n divided by 2 will be equal to our A, that is our total length. Therefore, we can say that our lambda of n will be equal to 2a divided by n. And in terms of linear momentum, we can just reformulate the equation. So we can say for linear momentum, let us suppose we call this as P of n, then we can write that our lambda of n is equal to over h upon the linear momentum, and we can write this as in the form of energy, that is equal to h upon twice m, and we have this as E of n and its square root. Lambda of n we already know, so we can say this will be equal to 2 of a multiplied by n is equal to h upon 2m E of n and its square root. So we can just solve this and find out our E of n. So we can say E of n will be equal to, we have this as n square and h square, this will be 2, 4 and 8, and we have m a square. So we only need the proportionality, so we can say E of n is proportional to a raised to power minus 2. So we get a raised to power minus 2. Option A is correct. Correct. And we also know that our linear momentum P of n is proportional to our m v of n. And P of n is can be written in terms of our a and n. So we can say our m v of n is proportional to, this comes as h upon lambda n, and this comes as h upon lambda n is our 2a upon n. So this comes as 2a and multiply by n. So from here we can say that our v of n will be equal to nh, and this comes as our 2ma. Therefore v of n is proportional to n. This is our part B. Sorry, not part B, that part C, sorry. This is part C. So option D is correct. D is correct. Let me write it, this is part C. And we have to find out the energy in the ground state. That is our part B. Energy, we already know the formula for E of n, and ground state is value of n is equal to 1. So let me write E of n is equal to n square h square, and we have 8m a square. Ground state is giving us n is equal to 1, so we get our E of 1 is equal to h square upon 8m a square. Now we already know the values, we substitute them. Our h is our 6.6, 10 to the power minus 34 whole square, and we this have 8. Mass is given as 1 into 10 to the power minus 30. Distance is also given to us, that is 6.6, 10 to the power minus 9 whole square. So we get our energy E1 is equal to, this is 1.25 into 10 to the power minus 21 joules. We can just convert into electron volt, 1.6 into 10 to the power minus 19, giving us 7.8 milli electron volt. This is close to 8 milli electron volt. So option B is correct. B is correct. Next question. It was asked in the year 2010, and it is also a passage based. It states that the key feature of Bohr's theory of spectrum of hydrogen atom is the quantization of the angular momentum when an electron is revolving around a proton. We will extend this to a general rotational motion to find quantized rotational energy of a diatomic molecule, assuming it to be rigid. The rule to be applied is Bohr quantization condition. So based on this, we have 3 questions. In part A, a diatomic molecule has a moment of inertia I. By Bohr's quantization condition, its rotational energy in the nth level such that value of n is equal to 0 is not allowed is. In part B, it is found the excitation frequency from ground to the first excited state of rotation for CO molecules is close to 4 by pi into 10 to the power 11 Hertz. Then the moment of inertia of CO molecule about its center of mass is close to. And part C, in a CO molecule, the distance between C and O is close to, and the respective mass in AMU is given to us. So we start with part A. In part A, we are going to use the rotational energy using Bohr quantization. And we already know that our Bohr quantization it gives us that the value of L is equal to n multiplied by the quantized value of our Planck's constant, that is h. And this can be written as that L is equal to n h upon 2 pi. And we also know that rotational kinetic energy of a rigid body rotational kinetic energy of a rigid body, if that is given as E, then this E will be equal to our L square multiplied by 2 times I. And we substitute into the Bohr quantized angular momentum. So we can write that Bohr quantized angular momentum and gives energy, that is rotational kinetic energy, that is for E of n. We substitute value of our L, we get this as 1 upon 2I, and this comes as our n square h square upon, this is our 4 pi square. So we can write that our rotational kinetic energy E of n will be equal to n square h square upon 8 pi square I. So we have our n square h square 8 pi square I. Option D is correct. N square h square 8, yeah, option D is correct. Is correct. Next, B part, we have to find out the moment of center of inertia for a carbon monoxide, that is CO molecule. And it is found the excitation frequency from ground to the first excited state of rotation of CO molecule is our moment of inertia. Okay, so our part B, we are supposed to find a moment of inertia, which is nothing but our I. Okay. And we know that the energy of photon will be equal to the difference between the ground level and the first excited state. So we are going to use that formula. So we can say that our energy of photon is equal to our energy difference between the ground level and the first excited state, and this energy of photon is our h times nu, that is our frequency. So we can say that our one second. Okay, this is given, frequency is given to us, that is our 4 upon pi. So we get this as h upon nu will be equal to E2 minus E1, and This gives us n2 and n1 giving us 4 minus 1, and rest of the things will be same, that is our h square divided by 8 pi square multiplied by I. So therefore we can say our I will be equal to, this comes as our 3h square, and here we have our 8 pi square h multiplied by frequency, that is our nu. This h goes with this square and we substitute the values. We get our value of I is equal to value of h is 2 pi into 10 to the power minus 34. So this comes as 3 into 2 pi 10 to the power minus 34. Here it is 8 pi square, and this comes as 4 upon pi into 10 to the power 11. So this pi and pi goes away, this 2 goes by 4, and we are left with 3 upon 16 into 10 to the power, this will be minus 34 minus of 11, that is minus of 45. This comes as 1.8, 7 into 10 to the power minus 46. So it comes as 1.87. Option B is correct. Correct. Okay, we come to now parts. Sorry, one part is left. Part C. And in part C, it states that we have to find out the distance between the two, C as well as our oxygen molecule. Okay. And for that, we are going to use the formula that moment of inertia for a CO molecule moment of inertia of CO molecule, which is our I, whose value we just found out is given as mu times r square. And here this mu is our reduced mass of CO molecule, and r is the distance between C and O, or which we can say as a bond length. Bond length. And this mu can be calculated is equal to, we have our m1 m2 divided by m1 plus m2. Respective mass are given to us 12, 16, and this comes as 12 plus 16 multiplied by 5 by 3 into 10 to the power minus 27. This comes in kg because it is given in AMU. And we already know that the value of I is already known to us. So from here we can say our R will be equal to R upon mu, or we can say R square is equal to I upon mu. Therefore we can write that our R square is equal to, we have our I is equal to, this comes as I we found as 1.87 into 10 to the power minus 46, and this is divided by 12 multiplied by 16 divided by 28 multiplied by 5 by 3 into 10 to the power minus 27, and we can just write it as multiply by 28 and multiply by 3. So we get from here that value of R is equal to 1.3 into 10 to the power minus 10 meters. Option C is correct. Correct. Next question. It was asked in the year 2010, and it states that an alpha particle and a proton are accelerated from rest by a potential difference of 100 volt. After this, their de-Broglie wavelength are lambda alpha and lambda p respectively. Then the ratio of lambda p upon lambda alpha nearest integer is. So we have to find out the ratio of their de-Broglie wavelength when they are accelerated through a same potential, that is our V. And the general formula for our de-Broglie wavelength that is our lambda is equal to h upon 2m q multiplied by V. V is the potential difference, which in this case is 100. We can just divide this formula into two parts and find out the ratio. Lambda p upon lambda alpha is equal to, we get this as h upon 2 mass of proton, charge on proton multiplied by V square root, and this comes as h, and this comes as twice mass of alpha, charge on alpha, and p and its square root. Here h and h cancels out, 2 V and V square root, along with square root they are going to cancel out. So we get lambda of p, lambda of alpha is equal to square root of m alpha q alpha divided by square root of m proton and q proton. And mass of proton, let us suppose, is of mp. So mass of alpha will equal to 4 times mp. So we can say that this is equal to 4 times mass of proton and will be equal to 2 times the charge on proton, and this is our mass of proton multiplied by charge on proton and its square root. So this mass of proton and charge cancel out, so this comes as square root of 8. So the ratio of wavelength for proton to alpha is our square root of 8, which is approximately equal to 2.8. Nearest integer we can say this is our 3. So option is 3 is the correct answer. So this completes all the questions. Thank you.